start this recording here. Okay, so by request, 10.1 question 2, write it in logarithmic form. Is it supposed to be 8 to the power of 3? I'll let poor Carson type that. Yeah. And then, yeah, so 8 to the power of 3, and then you should have log base 3. Sorry, not log base 8 of 512 equals 3. Yeah. Thanks, Zach. Okay, but I'll just say this, that the log of 8 times 512 is not the same as log base 8 of 512. So just be careful there. Let me know if it's still giving you grief though. Okay. That'll do it. Awesome. So just as kind of a review from chapter 10, we finished chapter 10 last week. But if we have something like this and we have to solve for r, right? R is in the power. Question 7. Let me see if I can pull it up here. Did you specify a part here? Log. Oh yeah. If you do the log base 10 of 10, log base 10 of 10, it's just going to be 1. And that's what it's showing. That's for A, right? Sorry, I can't actually see the chat. Okay, yeah, that'll do it. It should accept log base 10 of 10, but it doesn't seem to, so I don't know what's going on there, but. Okay, and then log x, solving for x. Okay, so I've got a couple by request here. I'll write them down so I don't miss out. Dermot had asked for question 1. Question 1 is actually in our notes, so you can have a look at the notes. But if we have, oops, the log of x plus the log of x plus 11 equals 2, okay, then I'm going to use that property that I can, if I have logs of the same base, we'll start with this one and then we'll do this one. How about? If I have the same base, then I can combine these as the log of x plus 11 equals 2. And then to undo this log base 10, oh yeah, I should put the, does anyone know what question number this is that we're working on? Oh, sorry, it's multiplying in here. Sleep on the job here. So this is 10.2, number 12. Okay. So then you have x squared plus 11x equals 10 to the power of 2, which is 100. You should just be able to use the quadratic equation, which is just going to be x squared plus 11x minus 100 equals 0. Remember, negative b plus minus the square root of b squared minus 4ac over 2a. So x equals these two values, where a is 1, b is 11, and c is negative 100. I'm gonna let you, does it, yeah. Michael keeps saying it in the chat. Remember, can't take the log of a negative number. And then, so I'll put it in here. Remember, we can't take the log, oops, hey, what's going on here? Of a negative or 0. So you'll probably get a negative number and a positive number, and only the positive number should be the result. Yeah, exactly. Yeah, so if it wants the exact solution, there could be some square roots in there. I'm not entirely sure. So you would just keep the square roots. Okay. So now, the original one that I said I would show you guys, move these up a little bit. Hey. Should have done these in order. Oh. We'll call this review, how about? So now if we're solving for r here, first thing we have to do is we have to get e to the negative rt on its own. And so that means we have to divide both sides by I sub 0. So I over I naught is e to the negative rt. And then to kind of undo the e, we have to take log base e on both sides. Log base e is just the natural log, I over I naught, which is negative RT. And then solving for R now that we've dropped that R downstairs, now I can divide both sides by negative T. And so I get negative natural log of I over I naught, or T is R. Let me just make sure, because we could expand this. I don't think it would want that. It wants it nice and compact. This would be the natural log of I minus the natural log of I naught. Let me just confirm here. No, it wants it to stay the way it is, so that we have it there. Okay. Hopefully, oh, my negative, you could have kept negative T down here and not had it up here. I always like to have the negative front and center so I don't forget about it. And so that's the only reason that it kind of, I floated it up from here to here. And so I kind of want to have this negative out in front of everything. But if you wanted to, you could definitely just say this. But it's a little bit cleaner if you kind of float it out front. Or like this if you wanted. Okay. So, just seeing if there's any more chapter 10 questions before we go to chapter 3. Chapter 3 this week. Chapter 3, so we won't do any more kind of review from chapter 10, but definitely if you're running into problems when you're doing these problems, then you can just text me and we can work through them. But chapter 3 is on logic. Sounds easy enough, right? It's not. We won't be going too deep into logic, but it can be a real bugger. Oh, are there any more proofs that we did not cover in class? I mean, a lot of those, so if you in the textbook, they do a couple more proofs, but they just apply those definitions that we had anyways. So I wouldn't ask you on a test to, hey, prove this just out of nowhere. I would warn you in advance, but you should be able to prove a lot of those things, or at least the ones in the textbook. We just did that one at the end, I think, I want to say. Last week, I can't remember. Okay, so let's see here. Oh, what I did just before class is I posted these notes, these logic notes in our, I want to make sure it's on our Moodle page. Because what I decided to do just today, actually, I was kind of sick of writing out all these notes. And so because there's a lot of definitions and a lot of just kind of stuff that we need to write down today. And so that's why I typed them up for you guys so that you can refer to them. And that way we can pick it up a little bit and just kind of go through and talk about stuff instead. Where did that note go? There. Because I just decided to type these things up earlier today, I did not get to 3.3. So we are covering 3.3. So I'll type up those notes and just kind of upload a new version of the logic notes with 3.3 added on. So don't worry, it'll all be there, but for today we have enough. All right, so let's see here. Last time I typed up notes for you guys, I don't know what I do it all the time where I just kind of steal notes and bring them into a note. With you guys, I was writing inside the note. It got really messy. So anyways, here we are. So we'll start with just talking about, so logic is reasoning, deductive reasoning is kind of, well, you know, if these things are true, then this must be true, right? We'll start with something really small, like a couple of statements here. So all humans are mortal. Socrates is human, therefore Socrates is mortal. Right? Very basic. We can all follow along, and we're just going to establish some terminology here. So all these things are arguments. Now I don't have enough room here. Whee! Didn't really. There. So these are all arguments. And the first two where we're just establishing, hey, here's some facts. These are called hypotheses. Oops, helps if I can spell it. Hypotheses or premises. Right, so we establish just kind of things that are true, and then of course we arrive at our conclusion. So this type of reasoning, right, where we kind of say, oh, oops, supposed to be in pointer mode. If we're establishing that all humans are mortal, okay, fine, everyone agrees. Socrates is human, okay, sure. Therefore, Socrates is mortal. So this type of reasoning is called deductive reasoning. Right? We're just deducing things that must be true. And then, so if the conclusion, right, follows from the hypotheses, we say that the reasoning is valid, right? So these are just some terms that we're going to be throwing around and that we need to kind of have a good handle on what they are. Okay. We're going to be talking a lot about statements. And so statements, there we go. So a statement is a declarative sentence. So something like, Mickey Mouse is president. True. Exactly. I thought that one was really funny, so I kept it. So a statement, and this is a kind of a definition of a statement, is a declarative sentence that's either true or false. So you have to be able to say that something is either true or false. So, wait, what was Michael's? Humans are featherless, humans are bipedal, therefore all featherless bipeds are humans. Invalid. But pretty good. So the conclusion is either going to be true or false, right? And so a statement, you have to be able to drill down and be able to say whether it's true or false, right? So something like 5 + 6 is 16, false, right? But it's a statement. And so Mickey Mouse is president, also a statement. It's either true or false. I'm not committing to whether it's true or false. Fish swim, again, it's either true or false. There's nothing in between. So these are all statements. Okay. These are actually called simple statements because they don't have any connectives, which we'll talk about in a little bit. But for now, they're just very brief, basic statements. And so, but if we talk about something like, what are you doing? That's not a statement. Well, it's a question. But it can't be classified as either true or false, right? And so that one's pretty obviously not a statement. Something that's harder, at least for me, to kind of pinpoint is if I say this sentence is false. I don't know if that's true or false, right? Because I don't know anything about Yeah. So it can't be classified as true or false. And sometimes they're a little bit sneaky, right? Are they statements? Are they not statements? I was flipping through some of the questions, and another one that kind of caught me was, what if we said logic is difficult? Well, it depends on what you're talking about, right? And so here, there's no strict true or false, right? Except for me, I would say true, but maybe you guys are going to say, no, that's false, right? And because there can be that, that kind of, all right, I'm using your word, subjectivity, right? Then it's not a statement. So not statements. So, let's see, I don't think I had to write anything extra here, so let's just go through these little bullet points, basically. So a compound statement is when we combine simple statements, right, with one or more operators or connectives. So things like not, and, or, neither, nor, if, then, unless, because, these are all connectives, or what we'll call operators. So I'll underline that here. Right, and so a compound statement is exactly that. It's just simple statements compounded together using some sort of operator. Okay. Just like a statement has a truth value, right? It's either true or it's false. We can find the truth value of a compound statement by looking at how these things combine. And so that's where we're headed in this chapter, which we'll just spend this week on chapter 3. So hang tight. So what we're going to do is we're going to just kind of talk about the rules for connecting parts. So using these operators, what does and look like? What does or look like? What does not look like? And that's where we'll start. And then we'll move to things like if, then, right? Statements. Okay. So for me, what makes logic difficult is being able to read an English sentence and translate it into different statements, which then I can translate into a logical statement or a logical argument. And then my goal is to simplify that potentially, and then translate it back into English. And so it's this kind of back and forth of going from English to kind of symbols and then back to English that can be really tricky. So we're building up to that throughout the week. So not immediately, we're going to start nice and slow. All right, so grab these. Maybe I should grab this too. So our most common, so statements can be false, right? They're allowed to be false. They're either true or false, but they have to be able to be classified as either true or false. Nice. Okay, so the conjunction. So in order to introduce the conjunction, P and Q are kind of our most common letters, right? We use letters like P, Q, R, S. And what you'll find is that a lot of this logic stuff, it'll kind of interplay with the set stuff that we talked about, right? So set notation, set operators, and or, etc. It's all going to look very similar, and that's because they are very similar. So if P and Q represent two simple statements, then P and Q is a compound statement, right, where I've smushed together two simple statements using the word and. And is called a conjunction. We symbolize it using this kind of, I don't know, caret style symbol. Okay. And so looks a lot like and in set operations, right? Looks like and, oops, from set operations or set operators, right? Except now it's pointy, so that's logic, I guess. Reading ahead to negation. I know. We'll talk about negation in just a little bit. Awesome. So if we have something like, I have a penny and a quarter in my pocket, then if we want to talk about when is this compound statement true, right, we need to figure out, okay, well, P and Q are going to represent these two simple statements where P is I have a penny and Q is I have a quarter. Okay? And then what I'm going to do is say that there are four logical possibilities. So if I have P and Q, and this is how we're going to start with everything that asks us, when is this statement true, right? Whenever we see something like this, what you're going to start with is you're going to start to develop a truth table. We're not going to call them truth tables quite yet, but what you're going to do is you're going to list all the possible outcomes of P and Q and the combinations of P and Q. Of course, if there's just P and Q, there are only four possible outcomes, four logical possibilities, and those look like this. P can be true, true, false, false. Now I'm doing just P because I want you to get in the habit of just always doing them like this. It's hard to think about, okay, well, what are my possible combinations here? And so if you always just have true, true, false, false for P, and then true, false, true, false for Q, you will have all the possible outcomes, right? So you don't have to put any thought into it. You can make sure, right? But now I've got true, 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 false, false, true, and false, false, right? Order matters because P is different from Q. If you want to bring it back to the set operations that we were talking about. Okay. And so if you always set up your truth tables like this, right, then you'll be safe. So here, always start your truth tables like this. So just kind of true, true, false, false, true, false, true, false. So here are kind of my possible outcomes, right? I think we can all agree that these are all the possible logical outcomes. And so if P is I have a penny and Q is I have a quarter, then what I can go through and do is I can just go through and talk about what these look like. So in words, true, true is I have a penny. The dog just came in. She's so excited. I have a penny. I have a quarter. Oh, get this over here a little bit because my sentences are a little bit longer. Make it match. I have a quarter. Okay. So we're not going to make fancy sentences here. In fact, notice that I'm not joining them up with an and because I don't have the and in there quite yet. We're not there yet. But if P is true and Q is true, well, I said and, but I have a penny, I have a quarter. That's the situation that's going on here, if both of them are true. And then, of course, if P is true, then I still have a penny. I have a penny. But then if Q is false, then I do not have a quarter. Now I don't have a penny, but I do have a quarter, right? And then finally, I don't have a penny and I don't have a quarter. I don't have a penny. Trying to write it nice and small. I guess I shouldn't say don't, it should be do not. I don't have a quarter, but I do have a quarter. Nothing happened. Now I don't have a quarter, or I don't have a penny rather. I don't have a quarter. Eee. Close enough. Okay. So, have you guys done logic in your other courses? Yeah? Like for this program or for a different program? Yeah, programmers love logic. They love it. And they need to, right? Of course, you have to have a good handle on logic, but it can definitely be a little bit tricky. Yeah, exactly. If this, then this. But we're just going to apply it to just kind of word problems and yeah, you could appeal to their emotional side. Yeah, we're going to talk about statements and translating statements, which is often what you want to do, right? In programming, you want to translate something into programming language. All right. So just as a little side note, just so you keep it in mind, the statements P and Q don't need to be related, right? So two statements like fish swim and there are 100 US senators, I'll take their word for it, is a true compound statement because both of these are true, presumably. Okay. So, which brings me to the definition of a conjunction. We talk about a conjunction, so that's and I'll make it nice and big here. Again, giant speak. I don't know any giant speak, but I'm glad I don't. Sounds terrible. So if we have statements P and Q, oh, fee, five, oh, from. So if you have, yeah, you could do, well, it kind of works actually, because it gives you lots of blanks. Like, I get it. Back to this truth table. So this is kind of our first official truth table that we're seeing. And so P and Q again, right, just like we set it up before and how I told you to set them up always, is you're going to start true, true, false, false, true, false, true, false. And then you've covered all your bases of all these different combinations. So then, thinking back to when we were talking about sets and how and behaved, the and behaves the same way for logic, right? And so if we have and in there, both of the statements have to be true in order for P and Q to be true, right? And so for all these other ones, true and false makes false, false and true makes false, false and false, of course, makes false again. Right, and so remembering what these look like, or at least how and behaves, is going to be really important, right? Because what we're going to do is we're going to build out all these huge statements, and we're going to apply just kind of true and true makes true, true and false, or any combination makes false. I think we stick to two statements. So just two arguments, potentially. I flipped through 3.3, but I think it is only, yeah, we stick to two statements. So that's good. Easy peasy. Yeah, but whew, also good. Truth table gets really long if you go for more than two statements, right? Let's say you have P, Q, and R, then you'd have 6 rows, right? Instead of just 4. Gets pretty big. So, so we can set up our truth table like this, and this is how we define the conjunction, which is and. Right, the word and. We can move on to the disjunction. The disjunction I've just kind of defined quickly here. Copy. So the operator or, right, it's denoted by a V, same or very similar to the U in set operations, right? Similar, oops, to U in set operators. So now we've got V for logic, kind of pointier for logic, I guess, but same idea, right? So or is a disjunction, which we denote by just a V. So one thing that we found, especially when we were working with sets, right, is if we say P or Q, Well, for sets, if we're talking about or, it's either P or Q or the overlap of the two, right? So that's what we call the inclusive or. Okay. A lot of people, when we first started with sets, you know, you didn't want to include that overlapping area, right? So what you were talking about was the exclusive or, which in logic is not going to be the or. So for us in this course, and you'll want to kind of check in if you do later courses, but for us, we're going to use the inclusive operator. So the inclusive or, where or means P or Q or perhaps both, right? Whereas if we want to talk about the exclusive or, then we'll say either P or Q, right? Either Q or P, whatever. So the either or is going to be separate, right? Because that's P or Q, but not both is either or. So that's the exclusive or. But when we just say or in logic, we mean the inclusive or, which is P or Q or both. So just like before, true, true, false, false, true, false, true, false, right? So our P and Q are set up the exact same every time, and you'll want to follow this structure. And then P or Q, well, if we're talking about the inclusive or, so either P has to be true or Q has to be true. So as long as one of those is true or both are allowed to be true, then we get a true result, right? And so true, true makes a true, right? True or false makes a true. False or a true makes a true, and the only time you get a false is if you have two false statements, right? False, false makes a false. False or false makes a false. Sounds logical. Right? So let's talk about negations and kind of how tricky they can be. Yeah, let's do all of this. So negation, we kind of saw negation with set operators as well, right? With the complement, right? That was the opposite of whatever set we were talking about. So the operator not is denoted by a squiggly line or this kind of hook, but I'm going to use the squiggly line. But in case you ever see this little hook somewhere, that's also a negation. Okay. I like the squiggly line, makes it, I don't know, it's nicer looking. And it's more kind of whimsical. And that's important in logic. So of course, we understand that the negation of a true statement is false and the negation of a false statement is true, right? Which symbolically is really easy to deal with, right? So these are easy kind of things that we can wrap our head around, right? If P is true, then not P is false, right? If P is false, then not P is true. However, right, it's a lot trickier to negate statements in language, okay? And so here are some common negations. Okay? So if we're given a word statement and we have to negate it, it's not always the way that you, try negating this statement. It's not always what you think it's going to be. Right? But here are some things, so some guidelines that we're going to use. So we're going to use these. If the statement has all in it, you're going to negate it by saying some not, right? All students are in this class. Right? Some students are not in this class, is the negation. Right? That's not necessarily where my mind goes if I have to negate all, but it is technically what the negation is. Okay, so you'll definitely want to have these handy somewhere when you're working on these problems. The negation of some is no, right? So some students take this class. The negation of that would be no students take this class. If the statement is some not, so some students do not take this class, the negation would be all students take this class. Of course, now you've just got a revolving door here, right? Because the negation of the negation is the statement itself. Okay. So some not, all, right? You should see that kind of link. And you only really need to memorize these first two. Okay. Okay, so looking at the assignment, I was working ahead here, trying to save time. So the assignment says all students wear hats, and then the negation is some students do not wear hats. So all students do wear hats, some students do not wear hats. Does that make sense? I know. It's not what we want it to be. A lot of the time, the negation is not, yeah, it's not the opposite of what we want, right? But the negation has to have the opposite truth value. And so that's where the negation comes from. Yeah. I know, logic. This is it. Doesn't seem logical, and yet here it is. So just remember, right, these ones are going to be really kind of important to keep in mind. I'm not highlighting these because they're the same, right, which I'll kind of same as above, since the negation of a negation is the statement. Okay. So I always like to kind of drill it down to the least amount of memorization that you have to do. There is some memorization that you have to do, but just kind of get the fluff out of there, right? And so here in math, the word some is used to mean at least one, okay? Which I'll kind of highlight in green here, because that's going to be really important. Okay, so if you're given sentences like you're finding if you're already working on the assignment, or when you're working on the assignment, it can be kind of tricky. Right? Oops, doesn't need to be quite that big. So if we want to write the negation of each of these statements, then we want it to be the exact opposite, but it's not necessarily going to be that, right? We need to figure out what that, what the kind of key word is in the statement, right? And so here, we're saying all. In the second one, we have some do not, right? And then no. Hey, what a coincidence. All, some not, no. Okay. But here we go. So all people have compassion. If we look at our table, right, all is going to negate to some people do not have compassion. All right, negation up here. Some people do not have compassion. You know what? Oops, there. Nice, Ashley. Ashley and Zach, killing it. Okay, so some animals are dirty. If we're looking at some, then we would have to replace it with no in order to negate it. So no animal is dirty. Some students do not take Math 10, so some not, or even if you wanted to go the reverse of some not here, makes all, right? So all students take Math 10. All students take Math 10. And then if our statement has no, then if we have to negate it, then it's going to be replaced with some, right? So no students are enthusiastic. We can negate it by saying some students are enthusiastic. Some students are enthusiastic. Okay. So negations can be very tricky. Symbolically, they're very easy, right? A false becomes a true and a true becomes a false. But in English, they can be very difficult, right? As we're kind of finding from the chat here. All right. We can still have order of operations, right? It's basically BEDMAS, but for logic. And so the order of operations, let's just talk about this briefly here. Ding, ding, ding. So parentheses are used to indicate the order of the operations, right? So we have to be really careful that we deal with stuff inside brackets before we expand out to outside brackets. So you want to go to your very innermost brackets and work your way out to figure out what the truth value is. Another thing to keep in mind, right, that if you have N and C, but the negation of it, right, that's, it is not the case that N and C, right? So N and C hangs together, even though it makes a weird sentence, N and C hang together, and then you negate that. Whereas if you just have not N and C, well, the negation is only on the N, and the C is just itself, right? So when you're reading these, the brackets really make a difference, right? So you want to be really careful with your brackets. Okay. So actually, I want to make a little note here. just like in, hopefully you guys remember BEDMAS, brackets, exponents, division, multiplication, addition, subtraction, right? Tells us how it's the order of operations for algebra, right? So just like in BEDMAS, the brackets will need to be read carefully. Will need to be read carefully in logic, right? Start with the innermost brackets and then work your way out. So start with the innermost brackets and work your way out. So let's see here. Of course. Here. Crop. I'll just put this information up here and this other information down here. Crop. So if we have something like, oh yeah. Two simple statements. I eat spinach, I am strong, awesome. Then we can translate these symbolic statements into actual word statements, right? So that's what we're gonna do. So we're gonna start with P and Q, right? So it's important that we understand, well, we know how to read these things, right? So we've got P and Q, not P, and then the negation of P and Q, not P and Q, not P, sorry, not Q. So we're going to translate these into words. So the first one, if P is I eat spinach, and Q, and I am strong, right? That's our statement. And there will sometimes be, or there will often be, I should say, sentences that we don't like, but I would probably stick with kind of weirder sounding sentences, because there's a risk that if you rewrite it, you change the truth value of the statement. And so there is that risk, unless you're really, really sure that you're able to change it without changing the meaning of the statement, then go ahead and do it. But sometimes I keep funky looking statements because it's just, I know that they're correct. So I eat spinach. Oops. And I am strong. The negation of P is I do not eat spinach. I do not eat spinach. Oops. Okay. And then the negation of P and Q, I have to be really careful, right? Because P and Q has to stick together. And so what I can do, and here's kind of one of those funny sounding things, is I would say something like, it's not the case that, that I eat spinach and I'm strong. It is not the case that I eat spinach and I am strong. So really like weird wording here, but it's technically correct. Okay? And so now if I want to negate the P, yeah, so, but it's not the case. And so the is not the case applies to both, right? So it's not the case that I eat spinach and I'm strong. Hard, right? So I would say this type of scenario is probably the hardest one to translate because you have to figure out how P and Q can stick together still, but then also negate it. Tricky. If I negate P, that's I do not eat spinach and I am strong, right? And Q, so I do not eat spinach and I am strong. Here we see a double negative, right? We already established in our notes that the double negative of Q, so not Q, is going to be, you can replace it with just Q. Often we have other words in our vocabulary that we can use, like we'll see here, right? But technically correct, if you just want to leave it nice and safe here, then 5 is I am not strong. Okay. For number 3, okay, sorry, I missed Riley's question. Yeah, so it's not the case, and then is gonna be, yeah, that I eat spinach and I'm strong. So it is not the case, and then you can imagine just kind of brackets around here. So it's not the case that I eat spinach and I'm strong. Oh, and then for number 3, looking at Zach's question here, so the statement includes all the cases where they are not both true. So you could still be strong or eat spinach, but not both. So for number 3 here, you have to be the opposite of P and Q, which is not the same as P or Q, or not P or not Q. So those aren't the same. Can I say I do not eat spinach and I am not strong? No, because you can't say not P and not Q, because that's separate. So this negation, it doesn't distribute inside. Okay. And I don't actually have the properties of how they distribute. But I will say this here is that not P and Q is not the same as not P and not Q. Okay. But then I'm kind of looking back at Zach's question here. So it's not the case that I eat spinach and I'm strong. So what I'm saying is I'm not the combination of those two. Which is different from what we want it to be. Mm-hmm. Anyways, this stuff, it's hard. Keep in mind, right, that these guys here must stay together in the negation. Oops. Oh. Complement of true, true. That's exactly right, yeah. But then, so if we've got true and true, and then the complement of that. Okay. I like what you're saying, Zach. I just want to be really careful that I don't tell you something false, ironically. Probably, I do like the idea of that, where you think of, okay, so if this is true and true, then the negation of that could be anything that's outside the set, if we bring it back to set theory. But that would include P or Q, not P or Q. Making a mess of this. Ugh. Yeah, your thinking works. I'm just trying to run it through in my head on the spot. It's hard. But if you're doing these, right, as long as you make sure that you treat this P and Q as its own thing, right? Yeah, P and Q is a single case. True, true. I like it. But then you have to negate it. And so here, the classic line for negating a lump of things is saying it's not the case that blah, 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 blah. Oh, let's finish this last one. So I'm not strong. If we say, so like I said, sometimes we have words that we could replace and make this look a little bit nicer, only if you're really, really sure of your meaning that you're replacing it with, right? And so, for example, not strong, we can assume that not strong is the same as weak, right? So then not Q is going to be the same as I am not weak. So if I am not strong, I can replace that with I am not weak. However, this, if you wanted to just stick with this, even if it sounds weird. So this is what I mean by, even if things sound weird, if you're playing it safe, I would just keep it here. I'm not strong. Great. And then if you're feeling confident, then you can replace it with I'm not weak. Right? Where weak is taking the place of not strong. Okay. So now, what if what if I told you that P is true and Q is false? Then what I want you to do is find the truth values for the statements. Yeah, not Q is just Q. You're right, Dermot. But I would probably still just leave it like this. It's a little bit nasty, but it's what this is saying, right? In our truth tables, then we can boil this down to just be Q. And I swear I've got a, here, I'll put it in. I've got this law of double negation here, which I'm actually going to slide into the notes here because it kind of fits in. Move it around a little bit. If I put it here. So if I have the law of double negation says that not P may be replaced by P in any logical expression. So then what we're saying is that not Q, you could just replace it with Q, which is I am strong, which is exactly what Dermot's saying. So, or, so not Q is the same as Q, which is I am strong. Replace it with not P. That'll make for a nice sentence. All right. So if we have to find the truth values, assuming that P is true and Q is false, what we're going to do is we're going to set up a truth table, which means, okay, I've got P in one column, Q in another column, and then because I know what P and Q are, I can really just go ahead and find what these things are together. So I don't need a table, even though I said a truth table, because I already know that P has to be true and Q has to be false, which is only one line on the truth table. So what I'm going to do is I'm going to write these out. So the first one was P and Q. Okay. So what I can do is I can replace P with true, and I can replace Q with false. So now I can look at a true and false. So here this becomes true and false. Right? True and false makes a false statement. So overall, this statement is false. Right? If we go back to what the statement was, I eat spinach and I'm strong. If I eat spinach is true, but I'm strong is false, then the statement where I say I eat spinach and I'm strong, well, that would be false because I'm not strong. Right? So for the second one, we had not P. Not P, remember P is true. Then, so not true is also false. Right? So what I'm doing here is I'm replacing these letters with the truth values and then seeing how those letters work in these operators. So here, replace the statements with their truth values. To find the compound statement truth value. So going to the third one, we had, that was that tricky one, right? The negation of P and Q. Okay, so the negation of P and Q, order of operations say I have to deal with what's inside the brackets first. So now I've got not true and false, right? P and Q is over here. I already decided that this is false. So if I wanted to, I could have skipped straight to replacing this with false, but we're not moving that fast quite yet. But so this becomes not false, which is true. The fourth one was not P and Q. So P is still true, Q is still false. So if I plug these in, so not true and false. False and false makes false. And then for that fifth one, which was not Q, we have to be careful here, not Q, even though we know it should be Q, so whatever Q is, that's what we should end up at. But let's just make sure. Not false. Not true, which is false. Same as Q. Right, which is what we needed it to be. Okay. How about we do another? Suppose N is a true statement and C is a false statement. What's the truth value of the compound statement? And here we have this big nasty. Ugh. We just got to take it slow and replace these things. So replace the N's with true and the C's with F, false, and then just kind of work from inside the brackets, moving our way out, right? So luckily we don't have to read a sentence and make something like this. That would be pretty gross, right? But we do need to be able to say, okay, well, once I have this logical statement figured out, what does it simplify to? Is it true or is it false? So we've got, I'm going to put it in the center of the page, and then I'm just going to fill it in just like we did up here, but now it's going to be way bigger, right? So we've got N and C in brackets, and not N and, oops, those look the same. N and, oops, a little for all thrown in there. Okay, hopefully I N or C and not N and C. Okay, ugh, here we go. Remembering that N is true and, well, I shouldn't say equals. N is true and C is false. Limits. Who likes them? Not me. So wherever you see an and, you're going to replace it with true. And wherever you see a C, you're going to replace it with false. Keeping these brackets because they're going to be really important. Limits are off limits in this course. So we've got true or false, and not true and false. Hopefully I did that right. Cheating looks, I don't know, too gibberishy so far. So we'll chalk it up as Michael's the only one who likes limits, but only as a means to an end. I hope. That's the only reason I like them too, and I don't really like them. I derive no fun from that. Derivatives are fine. Integrals, now those can be some nasty beasts, because there's not necessarily like any real structure. Sometimes it's like, well, it's because of this, which you've known from other questions. That's hard. Anyways, back on track. Dealing with inside the brackets first, right? True or false, as long as one of those is true, we have a true statement, right? And so here, inside these brackets, we've got true, and then outside we've got and then true and false. Well, because one of these is false, I've got a false statement. Kind of ballooning out, right? I have to negate this F first before I can combine it with the T, right? So I've got T and dynamite. T and T, dynamite. True. So this whole statement, whatever it is, whatever garbage this is from, right, it's a pretty big statement. Overall, if N is true and C is false, then the overall statement would be true. In the textbook, they have an example of reading a tax form. So, you know, weird things like, if this is true, then fill in this section. And if this is true, then this is false and whatever. So pretty fun to read. We're not going to do that one. It was way too big, but worth a look. So overall, this statement would be true. Nice. All right. So that would be kind of our basics, and, or, and not, right? Let's talk about, so in section 3.2, we'll talk about truth tables and the conditional. So I've said truth tables. We've made little truth tables, right, where we list all the possible truth values for P and Q, and then now we're going to build on those and start to figure out bigger truth tables. We're getting there. So the connectives and, or, and not, these are our fundamental operators, right? So those we have to have a really good handle on what they do. Of course, the not is easy. It's just the opposite, just like we want to think negation works, right? In words, that's not really how it works, but for truth values, it's the opposite. And both of those values have to be true in order for an and statement to be true. And for or, only one of them has to be true in order for the whole thing to be true. So we're going to need truth tables. And I guess I cut off my Oh, this example is so funny, and I'll tell you guys why in a little bit here. So this example says construct a truth table for the compound statement. And the compound statement is Alfie did not come by last night and did not pick up his money. However, if you read the textbook, and like I did many years ago, the first time I taught this, they don't actually have came by last night. It's just Alfie did not come last night and did not pick up his money. And then we negate it and we go through, and anyways, of course, I'm deciding they have the same meaning, but just kind of a funny thing to think about as we go through these, which I did in front of a class, kind of accidentally. I'm going through, I'm making my notes, I'm doing my thing. I'm like, oh yeah, that makes sense. Oh yeah, sure. And I go up there and, all right, so truth tables. Here's our statement. Oh no. Anyways, poor Alfie. Yeah. I know, it was terrible. But now I just think it's really funny. So anyways, here we go. I changed the statement slightly. So what we're gonna do, so constructing a truth table, we haven't talked about what this means, but constructing a truth table, clutching your pearls, it's really funny actually. It just means that we outline all the possible outcomes logically, as opposed to up here where we're given the logical values and then we find out what the truth value of the statement is. So here, what we're doing in a truth table is a truth table. A truth table lists all the possible logical outcomes in a table. Surprise, surprise. Okay. So first thing we have to do is we have to boil this compound statement down into just very simple statements. So we want to get rid of any negations, any sort of compounding, right? The and, for example. And so here, if we let this be sort of P and this be Q, okay. I put quotes around them because this is the negation, right? And so for my pure statement, Alfie came by last night, right? That's going to be my P, right? This is technically not P, right? The negation of P, Alfie did not come by last night. Okay. So, instead of air quotes, maybe I will use the negation. A little bit more proper. So what I'm going to do is I'm going to let P be Alfie came by last night. Oops, last right. And the statement Q is going to be Alfie picked up his money. Alfie picked up his money. Right? Notice that my statements are not going to have any sort of negations, right? So here, statements should not include, pun intended, not include negations. Okay. So what this statement is, right, is we have not P and not Q. So if we translate this, right? So then our statement, so the compound statement, I'll say, compound statement is not P and not Q. Okay. So what I want to do is I want to look at all the possible values of P and Q, right? Or those two together side by side, just like we did with if P is true, true, false, false, Q is true, false, true, false, to get all those different combinations. And then I want to build out to make this. I would encourage you to do it in as many steps as you feel is necessary. I would usually make a column of not P's, another column of not Q's, and then finally I'm going to build it out and have this full column where I can just look at the not P column and then look at the not Q column and see where they're true together. So this is step one. Step two, oops. And then finally, this is going to be step three. You can do it's something simple like this. You can do it all in one go. See here, I forgot an N. That happens. Okay, so what I've got is I've got P and Q. So here's my truth table. True, true, false, false. I had to scoot it up because I've got a page break here. And then true, false, true, false. This is how you're always going to start a truth table with two arguments, right? P and Q. And so this, remember, is your default kind of starting point. And then what I'm going to do is I'm going to make not P, right, where I just look at the column of P and I just negate it. So not P, oops. Not P, well, it's going to be false, false, true, true. False, false, true, true. And then I want to do not Q. Not Q is false, true, false, true. And then finally, what I want to do is I want to look at not P and not Q. But what I can do is I can just look at these last two columns, right, and see where they're true together. And so here, not P and not Q, false, false makes false. False and true makes a false. True and false makes a false. And true is the only time that I can get a true. So here, this is my first one, second one, and this is my third one. All right, so I would break up the statement that you want to make a truth table for, right, and into little itty bitty pieces that you can deal with individually, and then put them together to make this bigger statement. And so what we can see here is that the only compound statement, right, where it's true, is when P and Q are both false. Right? So you have to have P and Q both false in order for the compound statement to be true. The only time this compound statement is true is when both, oops, is when both P and Q are false. Okay. So let's get into, hey, I have another example here. Nice one. So if we have to construct a truth table to determine when this whole thing is true, right, we want to build it out little by little. So starting with the innermost brackets and working our way out, right, that's how we have to apply these truth values. And so starting again with just the column of P and Q, right? All our possible outcomes for P and Q, and then we just keep going from there. So P, Q, I'm gonna give myself a lot of space here because of course I'm gonna need it. So P and Q, P is true, true, false, false. Q is true, false, true, false. Standard setup. Okay. So now what I'm going to start with is I want to figure out, to be quite honest, because it's broken up with this and, I could deal with this one first and then go to this one. But what I'm going to do is I'm going to build this up and find P or Q and then AND it with Q to figure out what these values are. And then I'm going to deal with this one. But there are a couple of different ways that you could construct this truth table. So what I'm going to do is I'm going to have, this is my first column that I'm going to make. And then this is my second column that I'm going to make. This over here is going to be my third column. This is going to be my fourth column. And of course I could do these in any order. The green and the blues could be interchanged. And then finally, my final statement. I can smush them all together with the AND. Okay, so here we go. P or Q. Wait, you did it, Zach. It is not the case that Alfie came by and picked up his money and Alfie came by or picked up his money and picked up his money. It is beautiful. And that's only true if he didn't come by and he didn't pick up his money. Yeah. Alfie's gonna be poor soon. Okay. So, oh, Alfie. So P or Q. Let's deal with P or Q. P or Q is true as long as there's one true statement in the compound statement. And so we've got true, 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 false. Right? Just because of how we know how P or Q works. So then if we move on to P or Q, treating that as one thing, and Q, then we've got P and, oops, sorry, oops, switching it up here, P or Q and Q. Now I'm looking at this column and this column, right? The last two columns, I need to combine them with an AND. So that means I have to have both values of true in order for the statement to be true. So this is true, false, true, false. Okay. So that's good. So now I'm going to move over and deal with this side, which I could have dealt with first if I wanted to, because I don't join them up until later. But here it's important that you move from inside the brackets all the way out. Okay, so then if I do P and Q, remember which columns you're looking at. P and Q is only true if both statements are true. So true, false, false, false. Oops, make that false. All right. Now I'm going to negate this, right, which is really easy if I'm just looking at the truth values. Not so easy if Alfie did not pick up his money. Some money Alfie picked up. Just nasty. Not P and Q. Well, that's just going to be false, true, true, true. So now the overall statement, we can combine this column with this column, right, with the and. And so now, here we go. Let me just color code these a little bit. So here, this is 1, 2, 3, 4, and then finally 5, just in case I can't squeeze it all in here. Not P and Q and, oops, I made an A accidentally. And, oops, hee hee. This is where working on the iPad really helps, or any sort of surface. P or Q and bracket. We're all sick of Alfie now. All right, so I'm looking at this column, so the second column and the fourth column. Yeah, this is definitely going to be one of those things that, oh yeah, this makes sense. Oh yeah, sure, sure, sure. Open it back up. What happened here? So now I'm just looking at the second column, the fourth. Log jammed. Just have to be a little busy beaver. All right, true and false makes a false. False and true makes a false. True and true, woohoo, makes a true. False and true makes a false. True, I guess. So here, what we're finding, right, this is the only statement that's true. And so what we can say is that the compound statement is true only when, and then you're going to trace across here and say it's only true if P is false and Q is true. And this nasty thing is only true if Alfie did not come by, but he picked up his money. That's when the statement is true. So when P is false and Q is true. Okay. You would think so, but it depends on the other, but I don't know, I guess he could pick up his money some. Alfie's gonna get his money. I don't know about Alfie, but maybe they're two separate things. Who knows? Yeah. Dollar charge for some. All right. I think that's where we end today. So next day we'll start with the conditionals, which is if then statements, which I'm sure you're familiar with, right? If this, then that. blah, blah, blah. So, are there any questions? Logic, truth tables, oh, the ride. That's logic. All right. Well, I hope you don't change your minds about this all being fun when you're doing the homework, which I've posted. Yeah, one thing I've learned, I'll ask anyone if they've come by and pick up their money. Yeah, you got to find an Alfie first, and that could be tricky. Alfalfa. I hate you, Alfalfa. I named my first car Darla. Oh, Darla. Yeah, there's lots of Alfies. It'll be the new rage name. Archie, Alfie. You're the scum between my toes. All right.